Because next week's a break, when we come back, the Wednesday after that, we have an exam, which is on factor analysis, path analysis. Well, let's see, what did we cover in the last exam? We covered path. I gave you a concept list. Anyone with me? There was one that had a whole bunch of stuff. It had other things too. Manova. Here it is. We got a few of them, I guess. Two of them. Everybody got one to look at? You got one? There's also the structural equation one.
There's another one to talk about?
I need, yeah, that's this one. I gave it to you last night. I need one. Do you have another?
It's at home, it's fine.
Never did. Yeah.
I think I get one.
Take that one if you
Yeah,
can get one.
I have one at home.
When did you get that on?
Last time.
Done on a typewriter?
Oh, no, it's just an old one. Maybe it wasn't there. I don't know, I've had it a long time.
It's like an old.
I think we carved it in stone, actually.
Yeah, right.
Barney Rubble.
All right, so the concepts, we had some path concepts in the last test, right? I think we did. Sorry. There you go, right? We had some path concepts in the last test. I think we didn't cover interaction of regression in the last one. So we might have a couple questions on interaction. Remember, that's when you just multiply the two together, see if the two together multiplied or give you variance above and beyond the individual predictors. And then the way to, I mean, you don't need to know how to do it, but the way we did it was drawing graphs to see if there's an interaction for regression. Should be hard to do much more than a real basic concept with that one. And then for factor analysis, I'll give you output. You need to know the difference between confirmatory and exploratory, which is misspelled. Sample sizes, your book gives you some rules of thumb. You need big sample sizes to do these kinds of analyses. 20 to 1, maybe 10 to 1, things like that. There are different things. Difference between principal components analysis and factor analysis. The book does go into that in pretty good detail. The idea being, it's a little complicated, but they're using, the main difference is, technically, is that in principal components analysis, you're using a correlation matrix. 1, 2, 3, 4, 1, 2, 3, 4, and you have 1 on the diagonals and correlations on the off diagonals. So in principal components analysis, we take that correlation matrix and we use 1 of the diagonals and try to divvy up all of the variance in the model. So it's taking it and not just doing shared variance, but all the variance. In factor analysis, or any of the factor analytic techniques, we substitute in communalities for that 1, or shared variance. So we're saying we're not going to take all the variance, we're only going to take the variance that's in common among the items, and we're going to use that for the factor analysis. So instead of processing the data with all the variance with 1s on the diagonal, assuming that we've accounted for all the variance in each item. Remember what communalities are. They're the squared loadings across for each person. So if you take all the loadings, factor 1, factor 2, factor 3, and you get a number, square them across. If you get a number like 0.9, that means that almost all the variance in that item was taken up by a factor, some of them by the factors. If you got a 0.2, that means hardly anything. That item didn't load in any factor. Any of it got loaded. So in factor analysis, you only use the shared variance. In principal components, you use all the variance. Sounds like a big difference. In practice, it hardly makes any difference. Typically, I mean, they usually look quite the same. So as a matter of principle, most of us are doing things that are not too theoretical. We would use principal components analysis, not factor analysis. One of the kinds of factor analysis. But the book goes through that in detail. And it is a bit complex and theoretical of how they differ. But luckily, it turns out that in real life, it doesn't make too much difference. Rotations, pretty easy. We use quarter-max or pro-max or oblique rotations. That's where we keep we don't keep the axes perpendicular. We let them go on angles. Ferromax is the most universally used orthogonal rotation. So the concept is that you're trying to force the factors to be as independent from one another as they can, or you're willing to let them be correlated with each other. That's the difference between those two. Eigenvectors is just the name for the row of the eigenvalues. I don't think we're going to bother with that one, but eigenvalues are the squared loadings added up going down on the factors. So every item has a loading correlation to that one and the theoretical centroid. Square those and add them down. The higher the number, means the more variance is accounted for by that factor. And the number of items, the eigenvalue divided by the number of items is the percentage of variance accounted for. If you have 100 items, and your eigenvalue is 20, then it's 20 divided by 100. 20% of the variance is accounted for by that factor. The computer gives you that number, so you don't have to calculate it, but that's what it is.
And which numbers are you adding up to get your eigenvalues?
The loadings. Now, remember, we suppress the low ones, but those get added up too. Just to make it easier to see it, when we printed them out, we suppress the very low loadings. But that doesn't mean they're not there, they're just hiding beneath the link there. Okay. So, and then determining how many factors to retain is usually done by eigenvalues in some ways, because it tells you the importance of the factor. The screen test is one way to do it, just to plot them against the number of factors and see if there's a logical place to cut it off. You don't ever really get this, but if you got one of the screen tests that went like this, that would make it real easy, right? You know, the first three are important and nothing else is important. But usually they come down and they level off. Somewhere in those leveling off, you don't want any more of those factors. They're all counting for very little.
So at its peak is kind of when you cut it off, no?
No, it's the scree at the bottom of the hill. So generally they come down like that. So now it's somewhere like here or here, or here, somewhere like around there. You're making a judgment where to cut it off. It's not, you can't, there's no cut and fast rule for it. It's cut and dry. Mostly you kind of look at the factors and see if they make any sense and say, well, here's a 3-factor solution. I like these 3. The 4th one is kind of a mess. I don't like that one. I'm going to do a 3-factor solution. You keep on looking at the rotating loadings and try to decide yourself. Set of commonalities, I already said. So the main thing you want to know about commonalities is, did the item actually load somewhere? A very low item would mean it didn't load anywhere. Low commonality. And for factors retained, we just said the Kaiser criteria is a name for just retaining all of them with eigenvalues above 1. That's the default for the computer, but it's not necessarily the best one.
What's that called?
Kaiser criteria.
And can you repeat that again?
Just retain all eigenvalues above 1. Factor score, that's if you want to get data out of your factor. You've done the factor analysis, you're happy with your solution, done everything you're going to do, you tell the computer to save factor scores in the file. What it does is it makes a score for each factor for each subject. Essentially, it multiplies the person's score on all the items we have times the weights of those items. and gives you a single score, except it's in a standard score form. So that becomes the scale score. And you'd use that like in a factor, in a regression, in a ANOVA. Let's say you're doing ANOVA, you have a lot of independent, you have a lot of DVs, you do a principal components analysis, you decide that 5 of the DVs go together beautifully as 1. You come up with a factor score for that 1, make up a name for it, it's a latent variable, and then you compare men versus women, or treatment versus controls on that score. So when you translate it into doing something with it, it always has to be in the factor score form. Make sense? To kind of picture doing that. And you can determine whether loadings are significant or not, although most people don't really do that very much. And then for the SEM concepts, we've got path coefficients, betas, and semi-partials. Latent variables, we talked about a lot today. Oops, that should be measured variables, not measures variables, sorry, measured variables. Direct and indirect paths. So we talked about paths that were direct and indirect through another variable. Moderators and mediators we covered earlier. Remember, moderators change the relationship between one variable and another. They're not thought to be a causal link, they just modify the relationship. So like interactions. Mediators, we're trying to presume a causal link. A leads to B leads to C. And then we talked about Sobel tests or other tests for moderators and mediators, right? So how do you test moderators with multiple regression?
The direct path goes down.
No, that would be mediators. That'd be mediators. So if you look at, so in regression, if you look at A, C, B, and this path goes down when you have B, that would be evidence for mediation. For moderation, you don't do these pathways, you do interaction with regression. Right? Because it's the same concept as an interaction. Remember the one we did in class where we plotted them and saw that people who were high in dissociation and had intrusive thoughts following their trauma were much more likely to have trauma symptoms 3 months later. Remember that study? That was a real study. And it turned out that the combination together was more powerful than either of them separately. So that would be a moderation or an interaction effect.
So moderators give the causal link, mediators just interfere.
No, opposite.
Opposite.
Mediators are trying to move towards causal linkage. Moderators are trying to change. The classic moderator is hardiness moderates the relationship between stress and illness. Think of the one we did today. Right? There's a lot of data that shows that if you look at a relationship between stress and, let's say, and mortality. Age of people die based on stress. There's a relationship, right? But that relationship can be modified by people who have very high meaning in their life or high hardiness, right? So you look at people, like you look at people in the concentration camps, those who survived are the ones who attached some meaning to the experience somehow. They didn't give up. They somehow found a way of looking at this horrible experience in a way that they could conceive of. They could put a construct to it. And when you look at those people, they studied those people in Israel, they had better than average health. They survived this horrible experience, and that hardiness allowed them to get through this horrible experience with better than average. Whereas most people in the concentration camps who survived had died early, had terrible health, their lives were horrible. So they weren't the ones who weren't able to do it. So the moderator is somehow that cognitive structure that some people were able to put on this. And we wouldn't have thought that's a cause. The concentration camps didn't cause hardiness, which didn't cause illness. They have to look at it as a modifying relationship. Over identification, under identification, we went over today. book also goes over it. Lisserol, EQS, Amos are all programs for structural equation model. Last time we did the reproduced correlation matrix, remember? That was a question everybody missed. So I might ask that again.
Say it again.
Remember when you multiply the correlations on the direct paths to get a reproducible thing, and then you look at the original correlations versus the multiplied ones? It's in path analysis chapter, you can look at it. I guess I asked it last time, but I might ask it again since everybody missed it and I gave you credit.
I got that one right. Now the trick is to not.
Yeah, second.
Since last time you said that the chapters for this test were off on the syllabus, could you say which chapters in the book are you dealing with?
Question. So, the path analysis chapter. So this time we've got exploratory factor analysis. I'll give you the chapter number. I mean, principal components, that's chapter 12A and 12B would be the main one. This could be the main part of the test, 12A and 12B. And then there's also some on the exploratory one, confirmatory, which is 16A and B. And then 17A and B is the path analysis. So those are all getting covered somehow in here. And 18A and B is structural equation modeling. So although really those last 4 chapters just kind of do the same thing with and without latent variables. They kind of repeat the same idea. There's not a ton of concepts in there, it's mostly just sort of how to do it.
This top part is also going to be on this test? The COBA?
No.
Just the middle?
Just the middle, yeah. Yeah, we got to ANCOVA yet, or we're logistic.
You're going to cover anything on the previous test, or it's just this?
No, just this. So I'll give you some factor analysis output, ask you a bunch of questions about it, ask you some general questions about structural equation modeling and path analysis. There's not a ton of questions on those because there's not that many concepts. And that's it. Okay?
Question. Again, this last concept that you said a lot of people missed, can you explain what you're, explain more?
I gave you a whole handout on it, remember?
Oh yeah, I read it, it was very complicated.
Yeah. I'm not going to ask you to do one, but the idea is that if you have a path analysis of some sort, direct and indirect paths, what you can do is take the path weights, the betas, and multiply them times each other,
Yeah.
and get a series of correlations that you compare to the original correlations from this is A, B, C, D. So the correlation between A and D, you'd look at the original correlation just between A and D alone, and then you'd look at it with 8, this one times this one, times this one, times this one, times this one, to see if it matches that correlation. That's a way of fitting those path analyses.
Okay.
So there's nothing in detail about it, just a way of testing a path model is with reproduced correlations. I'm not going to ask you to do one because they are complicated. And if you look at just the beginning of that handout I gave you, it kind of gives you the idea. I don't think the book does, this version of the book didn't do those, I don't think. No, they don't.
Is there ever an instance where it is the same?
Yeah, if they're the same, then it's a good fit. If they're not the same, remember I gave you the example where we looked at one that was a good fit, one that wasn't a good fit. We might want to modify the model if it's not a good fit. It's the way people, before structural equation modeling, this is how people did this stuff. Before they had computers that would do these fancy ways we do it with all the graphics and stuff. So if you think about it, it just kind of makes sense out of the moderator meter kind of idea. Okay, have a great spring break.
Thank you.